So the last thing we're going to look at here is we're going to look at the idea of regulating pH within the body through the various buffering systems that we're going to be dealing with. When we look at the pH buffering within the body, we have to remember a very simple thing. We want to stay within a range of about 7.35 to about 7.45 in terms of pH. Anything outside of those extremes within a small bit will lead to death, regardless of how we want to talk about or look at various products that we might consume or what people might tell us that we might want to try to consume. Your lungs and your renals do a very good job of ensuring that we eliminate any of the excessive acids that we might be building up, as well as maintain the proper amount of alkalinity within the body through the maintaining the anion gap or through the bicarbonate shovel. You do not need to consume excessive amounts of alkaline solutions. In fact, over-consuming alkalins is actually very bad for you, as we'll talk about here when it comes into playing with acid-base buffering issues. So what is the idea of the acid-base regulation? Well, what we're trying to do is we're trying to maintain a normal pH value of somewhere between 7.35 and 7.45. This is primarily done in an attempt to neutralize metabolic waste, but we're not really neutralizing the way that we think about neutralizing it when we look at chemistry. What we're attempting to do is we're attempting to make sure that we have a dynamic equilibrium within the bicarb processes within the body, in which when CO2 exits from cells and enters into the plasma, it's going to interact with the water in the plasma to form carbonic acid. Carbonic acid will dissociate into its anion and cation, respectively, the bicarb HCO3 negative and its cation H plus. As we start having more metabolic activity, there's an increase of CO2 within the plasma, which is going to shift the dynamic equilibrium towards the increase of acidic conditions, meaning we're going to start having more H pluses possibly within the plasma. The other thing that we look at when we look at this acid-base buffering is what's referred to as the anion gap. The anion gap is the difference between the cation within the solution and the anion within the solution, where we're going to have a greater negative ion within solution than a positive ion within solution under normal conditions, which is how we're going to be able to keep pH at the physiological range of 7.35 to 7.45. So what are the principal sources for acids coming into solution into the plasma? Well, we're going to get it from glucose metabolism. We're going to get it from any of the free fatty acids or from any of the metabolites of free fatty acid metabolism, such as ketones. We'll get it from amino acids. We'll get it from the metabolites of amino acid metabolism, such as ketone formations or ketogenic amino acids going into circulation. All of these will be able to donate hydrogen ions or electrons, more precisely, into the solution while it's in exposure with the water in the plasma. Under normal conditions within the cell, most of these substances will not actually cause changes of pH because there's not enough water within the cell itself to induce the acidification reactions. However, once we're in the plasma where we're interacting with a solution that is 90 to 95% water, we now have additional water molecules to interact with so as to allow for the dissociation to take place. On the other side, what things are going to cause an alkaline change? Well, things losing acids will cause an alkalinic change. Overaccumulation of buffers, overconsumption of alkalinic solutions, overutilization of pharmaceutical agents, or having adrenal issues can all cause alkalinic conditions. Hypoventilation can also cause alkalinic conditions. Acute mountain sickness can cause alkalinic conditions. So when we talk about these issues of alkalinity versus acidity, what we're actually talking about is we're talking about the willingness for substances to either allow for hydrogen ions to move into the solution, or more importantly, have molecules in solution that will donate hydrogen ions or electrons into the solution when they start interacting with water. Whereas when we have an alkalotic condition or alkalosis, what we're doing is we're having substances that are more willing to accept hydrogen ions or electrons from the solution when they're interacting with the aqueous environment. And so what we're going to do here is we're going to take a look at what are the various conditions that we're going to be dealing with as it relates to alkalosis and acidosis. And the whole thing here is what is the concentration of H2CO3 or HCO3 negative within the plasma relative to the normal levels that it should be at, along with what is happening to the CO2 levels in terms of PCO2 that we see. So when we look at this, we basically have this framework of schematic to look at in terms of what happens in terms of do we have an elevated level of H2CO3 or HCO3 negative. If we have this elevation, we now have to look at what happens to PCO2 levels, in which we can have one of three options. We can have a reduction of PCO2 levels with an increase of pH. We can have no change of PCO2 with an increase of pH. We can have an increase of PCO2 with variable changes of pH. If we see a decrease of PCO2 with an increase of pH, we know that we're dealing with a metabolic alkalosis and a combination with respiratory alkalosis. If we see variable change with PCO2 with an increase of pH, we know that we're dealing with metabolic alkalosis and possibly a respiratory alkalosis. If we see an increase of PCO2 with a variable change of pH, we know that there's something going on in between what's happening metabolically with what's happening respiratorily. In which, if we're not exchanging enough CO2, where we're seeing a variability of pH, we could have very easily get respiratory acidosis. Something happens when we have hyperventilation taking place. Or we can have a metabolic alkalosis taking place. On the other side of this option, we could have a reduction of H2CO3 or HCO3 negative. If we see this reduction with a reduced PCO2, we could have variable pH levels. We could have a no change of PCO2 with a reduction of pH levels. Or we can have an increase of PCO2 with the reduction of pH levels. If we see a reduction of PCO2 and a variability of pH levels, there's one of two options that can be taking place. It could be metabolic acidosis, where we're accumulating more metabolic products within the plasma that could go about donating hydrogen ions, or we can be having hypoventilation, leading to a respiratory alkalotic condition. If we see no change of PCO2 with the reduction of pH, we know that we're dealing with acidosis, and this acidosis can either come from metabolic conditions or from respiratory conditions. If we see an elevation of PCO2 and a reduction of pH, we know that we're dealing with a combination of metabolic acidosis and respiratory acidosis. The other way of looking at this issue is what are the root causes of what's going on? So, what happens if we have acidosis? If we have acidosis with a increase of PCO2, we're primarily looking at a respiratory cause. If we're looking at acidosis with a reduction of PCO2, we're primarily looking at a metabolic cause. If it's respiratory with an elevation of PCO2, the principal causes are going to be some sort of airway obstruction, acute or chronic lung diseases, overuse of sedatives, or weakness of respiratory muscles. This is where we're not getting very good gas exchange going on, where tidal volumes are very low, but respiration rates may be very high. If it's metabolic acidosis, however, what are the root causes? Well, we have to look at what's happening to our anions. If we have a high level of anions, It's usually in association with having some sort of toxicity going on, where we're either over-consuming methanol, we have a uremic issue, where we have too much urea within the plasma. We have diabetic ketoacidosis, where we have both high levels of ketones as well as high levels of glucose within the plasma. We have lactic acidosis, where we have excessive amounts of lactate in circulation with excessive amounts of glucose in circulation. We have overconsumption of salicylates, or we have overconsumption of ethylene glycol, which is one of the root metabolites of oxaloacetate, OAA. However, if we happen to have normal anion concentrations, the root causes here seem to be either loss of or issues with clearance of the acids as opposed to the accumulation of acids, where we're going to look at things like diarrhea, renal acidosis, hyperkalemia, or ingestion or inhalation of aerosols. On the other side, we have an elevation of pH where we start getting alkalosis. If we get alkalosis with an elevation of CO2, we know that we're dealing with a metabolic cause here. And this metabolic cause is predominantly from a loss of acids. This loss of acids comes from consumption of diuretics, excessive vomiting, excessive antacid consumption, or an issue with the adrenals with hyperaldosterone. On the other side, if we have a reduction of CO2 with alkalosis, it's primarily a respiratory issue and it's primarily due to hypoventilatory changes. These are the same changes that we see when we have acute mountain sickness or early altitude exposure. We can also see this with excessive aspirin ingestion due to what the salicylic acid consumption will do to the buffering, increasing the rate at which buffers are being produced so as to neutralize the excessive aspirin consumption. The other thing we can look at is what happens with alkalosis. One of the things that can happen with alkalosis is the loss of fluids due to excessive vomiting, where we are going to not be able to recoup some of the acids, but we will still be recouping bicarb through reabsorption principles, in which we're going to, by reabsorbing the bicarb but not reabsorbing acids, what we're going to do is we're going to initiate a metabolic alkalotic condition. So those are the cases for acidosis and alkalosis, but how does the body go about taking care of this? Well, we take care of this through our buffering systems. Our buffering systems act as weak bases or weak acids following the principles of Lewis and Bromstein's acid and base reactions, in which we're not really substances that are going to be true acids and true bases, but what we are is they're molecules that are either willing to accept electrons or hydrogens or willing to donate electrons or hydrogens into the environment. We have three principal systems that we're going to look at. We have the protein buffering system, the bicarb buffering system, and the phosphorus nitrogen buffering systems. Principally, these are going to function alkalinically in terms of being a buffer, which means that we're better set to deal with acidosis than we are to deal with alkalosis. They're both bad. However, alkalosis is much worse than acidosis. So the first system that we're going to look at is what's referred to as the protein buffering system. The protein buffering system is the principal buffer that we see within the intracellular fluids. In this, the carboxyl end can act as an acid, the amine end can act as a base, and the side chain can either act as an acid or a base. It can do this by accepting or expelling hydrogen ions and their associated electrons in order to temporarily neutralize the molecules that are willing to either accept or donate hydrogens into the environment based on what they're interacting with. Within the plasma, we have two types of proteins that will come about that can act as buffers. However, the principal buffer in the plasma happens to be the bicarb shuffle. The two plasmal proteins that we look at are both hemoglobins, and these are the carboxyhemoglobin and the deoxyhemoglobin. And we'll look at deoxyhemoglobin here in a second when we look at the bicarb. So bicarbonate is going to be the principal buffer that we see within the plasma, in which we're going to use the weak acid, the bicarbonate ion, and or the weak base, the bicarbonate ion, or the weak acid, the carbonic acid, in order to maintain normal pH levels and the normal anion gap, in which the erythrocyte, the RBC, can go about increasing the amount of bicarb in the plasma using a dynamic equilibrium reaction that is catalyzed by carbonic anhydrase, in which diffusion of CO2 into the erythrocyte leads to the formation of carbonic acid. Carbonic acid, when there is excessive acids in plasma, will dissociate into its buffer bicarbonate ion, which will diffuse into the plasma. As it diffuses into the plasma, chloride ions will diffuse into the erythrocyte. This is what's known as the chloride shuffle. What the chloride shuffle is going to do is it's going to ensure that the anion gap stays stable. However, we have a much stronger buffer in the bicarb ion than we have in the chloride ion. The hydrogen ion that was associated with the carbonic acid will now associate with the hemoglobin. It's going to associate with the hemoglobin, dissociating the oxygen molecules on the iron. This oxygen will diffuse into the plasma, forming the deoxyhemoglobin molecule within the erythrocyte. This shuffle, in terms of the increase of bicarbonate within the plasma, is why we get the right shift under carbonic acidic conditions or under acidic conditions within the plasma that we saw with the oxyhemoglobin curve. The last two of the shuffling systems are going to be acting as a cation catalyst, and these are the phosphorus system and the ammonia system. The phosphorus system and the ammonia system are going to be seen within the renals and within the liver, in which what's going to happen is that the excessive cations will be able to link onto the phosphates, forming a dihydrophosphatic molecule that can then be excreted into either urine or bile. The other thing can happen is that the phosphates can donate out the hydrogens, allowing for an increase of cations within the solutions, so as to buffer for anything that is excessively alkalinic. The ammonia or the ammonium buffer works the exact same way, in which it's going to be coming off of the amino acid metabolism more than the cation issue that we see with normal metabolic buffering that we see with phosphates, in which the ammonia is going to come from the amine through transamination and deamination principles. That ammonia is going to be able to link onto a secondary cation forming ammonium that can also go about within the amine group, combining with the carbonic acid to form urea, where we combine it just with the CO2, or uric acid if we were to combine it with the carbonic acid. These will then go about being excreted from the kidneys in normal urine production processes. So how does this go about functioning in terms of within the renals? The cycle of bicarbonate allowing for us to buffer within the renals using both ammonia as well as phosphates. What ends up happening is that as we start to accumulate carbonic acid within the plasma, we're going to allow that carbonic acid to be translocated into the luminal cells, which will then dissociate into the hydrogen ion as well as the bicarbonate ion. The bicarbonate ion will then be allowed to move back into circulation to accept more hydrogens to come back as carbonic acid. The hydrogens will get pumped out of the luminal cells into the nephron tubule via a sodium hydrogen antiporter. The hydrogen will then link on to the phosphate or the amine in order to form either the sodium hydrogen phosphate or go ahead and form ammonia or ammonium, which will then get excreted as urine. What all the buffering is attempting to do is attempting to allow for normal pH to be maintained by maintaining the normal anion gap. The way in which we can look at this whole schematic feed out is what are the two compensatory mechanisms that will play out as it relates to the issue within the maintenance of pH, where when we start having a reduction of pH, chemoreceptors both centrally and peripherally would trigger two things. They'll trigger from the pneumotaxic centers the triphasic response within the ventilation, which is going to increase ventilatory volumes, minute ventilation, in order to increase the rate at which CO2 and hydrogen ions are being released. Within the nephrons, we're going to increase the antiporter secretion of hydrogen ions and reabsorption of sodium. This is going to lead to retention of water within the plasma to allow for additional carbonic acid and additional bicarbonate formation within the plasma. We'll also be able to form more ammonia and ammonium within the nephron as well as within the liver to allow for continual excretion of those two substances either in bile or in urine in an attempt to reduce both carbonic acid as well as hydrogen ion concentrations within the blood by eliminating the metabolites that are willing to donate the hydrogen ions into solution. Now we have to remember that all of these buffering systems and the response that we see both renally as well as pulmonarily are all meant to be a temporary fix to the problem. They are simply binding on in order to eliminate the metabolites that could be acidic. It's very similar to the antioxidants, temporarily binding onto the ROSs until those ROSs can be stabilized.